Hi, today we're diving into the world of encryption and unraveling the mysteries behind one of the most widely used security protocols, AES encryption. In this video, we'll break down AES in a way that's easy to understand, even if you're not a tech expert. Whether you're a student, a professional, or just curious about how data stays secure in our digital world, this video will give you the insights you need. AES is the Advanced Encryption Standard. It begins with the key expansion, in which round keys are derived from the original key. The plaintext will then go through a number of rounds, depending on the size of the key, where each round consists of 4 operations: subbytes, shift row, mix columns, and add round key. The text will then go through one final round, which does not include the mix columns operation. This process is done for each 128-bit block of plaintext, and the generated ciphertexts are then recombined to create the final encrypted ciphertext. In this video, we will go through each and every step so you can understand exactly what is happening when using this method of encryption. Let's start with the key expansion. Our initial key, that we shall call K0, is 128 bits long, represented here first in binary, then in hexadecimal values, each of which contain 8 bits of information, and then placed into a 4x4 matrix called a state array. Each round of encryption is going to use a different key, with the number of rounds determined by the length of the key. To get the key for the next round, we take the last 4 bytes, or 32 bits, of data in our array. We then take the top byte of our state array and move it to the bottom, forcing each of the other bytes to shift upward. Every byte is then substituted with the corresponding byte from a table known as an S-box. The first character of each hexadecimal value corresponds to the y-axis of the S-box, while the second character corresponds to the x-axis. For example, the hexadecimal value of CF corresponds to a y value of C and an x value of F. This gives us the new hexadecimal value of 8A. This process is repeated for each of the 4 bytes. Next, we add what is known as a round constant. A round constant is a fixed number that is added during the key expansion phase. The first round constant is always 1, and it will double each round. So, the round constant for the second round will be 2, then 4, then 8, and so on. This continues to a maximum of 255, at which point a fixed value is deducted to always keep the value within the allowed range. The way we apply the round constant is by using an XOR operation. XOR stands for exclusive OR, and it's a logical operator that states if the 2 inputs are the same, then the output is false, 0, else true, 1. First, we need to convert our hexadecimal values to binary. Then, we compare each binary digit from our key value to the corresponding digit from the round constant. If both values are the same, then the output becomes 0, otherwise it becomes a 1. We do this for each of our 4 values and then convert it back to hexadecimal. Now, we go back to our original key, K0, and take the first 4 bytes. We then run these through an XOR operation with the values from our previous operation. The result gives us the first 4 bytes of our next round key, K1. Then, for any new column x of the new key, we XOR column x from the previous key with column x-1 of the new key. In other words, to calculate column 2 for K1, we XOR column 2 of K0 with column 1 of K1. To calculate column 3 of K1, we would XOR column 3 of K0 with column 2 of K1. And to calculate column 4 of K1, we XOR column 4 of K0 and column 3 of K1. This gives us our completed round key, which then serves as the starting array when calculating the round key for the subsequent round. This entire process is repeated over and over to generate all of our round keys. In this case, we are using a 128-bit key, so there will be 10 rounds, and therefore 10 round keys plus our original key. Now that we have all our round keys, we can move on to the encryption process. Here we have 128 bits of plaintext, again represented in hexadecimal, and then transferred into a state matrix. Before we begin the first round of encryption, we need to apply the initial key, K0, to our plaintext by using an XOR operation. This gives us the result matrix, which is then ready to begin the 4-step process of each round. The first step of each round is subbytes, in which each byte is substituted using the S-box. The process of substitution is identical to when we were doing the key expansion. The second step of each round is the shift row. The second row is shifted to the left by 1, the third row by 2, and the fourth row by 3. The overlapping bytes are then transferred in from the right, so we end up back in a 4x4 matrix. Step 3 of the round is mix columns. For this step, we take the first column of the state matrix and isolate it. This is then multiplied against the first row of the multiplication matrix. This is by far the most complicated step of the round, so let's break it down. Consider it in general terms first, where each byte of our first column is represented as B0 through to B3. We then have our multiplication matrix, which includes only the values of 1, 2, and 3, and the order remains constant. On the right-hand side, we have our equations that we are going to use to get our altered bytes, represented as D0 through to D3. You can see from the colors in the top row where I have inputted our constants from the multiplication table. The equations contain two operators, multiplication and addition. However, these operators work differently within a Galois field than they would normally. Addition in a Galois field is done through the XOR operation that we are already familiar with. Multiplication involves several steps. To demonstrate how it works, I'm going to go through the entire conversion process from B0 to D0. First, let's do some conversions. We are going to replace our generic B variables with the actual hexadecimal values from our state array. Then, we are going to convert those hexadecimal values into binary, and finally into polynomial expressions. The conversion process is quite simple. Start with the leftmost binary digit. That digit becomes the coefficient of x to the power of 7. In our top row, the first digit is a 1, so the first part of the polynomial becomes 1x to the power of 7. Then take the next digit. This becomes the coefficient of x to the power of 6, and so on and so forth. Then, remove any values with a coefficient of 0, and we have our simplified polynomial expressions. It is important to note that at this stage we have not changed these values at all, we are simply converting them between different forms. Next, let's take our constants from the multiplication matrix, which remember are the values of 1, 2, and 3, and convert those in the same way we did our variables, first into binary and then into simplified polynomials. Now, let's take our equation for converting B0 to D0 and replace all our B variables with our polynomial expressions. Then, let's do the same thing with our constants. That is a long equation, so let's break it down into 4 separate components denoted by our red, green, blue, and purple sections. Multiplication in a Galois field has 2 basic steps. The first is polynomial multiplication, and the second is division using the reducing polynomial as the divisor. We shall refer to the reducing polynomial as m, and m is a constant set as x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1. We start with the polynomial multiplication. We then want to convert this back into binary form. The problem is that binary numbers contain 9 digits, and our Galois field only allows 8 digits. In other words, we can only have values between 0 and 255. That's where part 2 comes in. Let's convert m to binary. We then divide our variable by m until we have an 8-digit binary result. This is done using the XOR operation. If the leftmost digit is a 0, we can eliminate it, and we are left with an 8-digit binary number. That is the red section of our equation complete. Moving on to the green section, we follow the same process. We multiply our polynomials together, but this time you'll notice a difference. Unlike in normal polynomial multiplication where we would collect like terms, in a Galois field they cancel each other out. As an example, take a look at the third row. Normally, we would combine our x to the power of 5s from both brackets, and our final expression would include 2x to the power of 5. But in a Galois field, those x to the power of 5s cancel each other out, and we are left only with variables that have a coefficient of 1. The next step is identical to the red section. We take our constant, m, and use it as the divisor for our green variable, using the XOR operation to arrive at our 8-bit binary value. Because our blue and purple sections are both just multiplied by 1, and therefore do not change, we can skip all of what we just did for the red and green sections and just put in our binary values for B2 and B3. This gives us our final values ready to XOR. We do this from left to right, so we XOR red to green, then the result of that operation into blue, then the result of that operation into purple. The output of that gives us our final binary digit, which we can then convert back into hexadecimal. In our case, the final digit is 4, which is also written as 04 in hexadecimal. If we go back to our original equations, we can now replace B0 with our original value of D4, and our first resulting variable of D1 with the hexadecimal value of 04. The same process is followed for each of the other bytes in the column. The only thing that changes is the order of the constants from the multiplication matrix. All that's left is to add the round key. Just as we did before beginning the first round, we can add the key using the XOR function. This time, we are at the end of round 1, so we will use K1. That gives us the final result matrix for round 1. The number of rounds used for encryption depends on the size of the key. We are using a 128-bit key, so there are 10 rounds. Each of these rounds is identical except for the very last one, which skips the mixed columns step. You can see our initial plaintext, followed by the result of each round and our final ciphertext. So there you have it, every step of the Advanced Encryption Standard. I hope you found this video helpful, and if you did, leave a comment with the next encryption algorithm you would like me to cover.